you can hear at the back. I'm not going to shout. Good. Thank you. Okay, the red light has appeared, so maybe we should start. Our last few people. If you have an empty seat to your left, can you shift up just to allow the last few people to squeeze in, because we're nearly full. So thanks very much, everyone, for coming today. So my name is John Roiser. I'm a cognitive neuroscientist from University College London. And I'm really delighted to be here. It's a great honour to be able to give the annual Birrell Lecture, and welcome to members of the family. And I have been interested in mental illness ever since I was an undergraduate student studying psychology. And the more I learned about it, the more confused I became. And I got to the point where I thought, really, we're going to need to use the latest psychological techniques, latest neuroscientific techniques in order to understand what's going on in people's minds, what's going on in people's brains. And that's basically what I study. I study what's going on in the brain and what's going on in the mind of people when they suffer from mental health problems. And I have chosen mainly to work on depression, and so I'm going to mostly talk about depression today, in part because I think it's probably easier to understand than some other mental illnesses. I'm going to talk a little bit about schizophrenia, or rather one symptom of schizophrenia as well, towards the end, but I'm not going to talk about my own research there. And I was always fascinated by schizophrenia, but it was always just very, very hard. It was very hard for me to wrap my head around what could possibly be going on, whereas I think we might have maybe a slightly better traction and maybe some easier questions to answer in the area of depression, and I hope in the long run some potential for clinical translation as well. So the title of the talk is Computational Psychiatry Towards a Mathematically Informed Understanding of Mental Illness, and the title is the same name as a paper that I published with some colleagues a couple of years ago, and it's basically trying to apply some of the computational work which has been brought into neuroscience over the last 20 years or so in different sorts of settings, and figure out whether we can use this kind of approach, which really relies on a heavy amount of computing hardware and software, and which in many cases only really become feasible in the last 5 or 10 years in terms of the amount of time it takes to estimate the models and provide useful estimates, and bring that kind of technology to bear on understanding mental illness and its treatment. So that's what I'm going to try to talk to you about today. So I think probably people are coming from different sorts of backgrounds here. So I'm going to do a brief introduction about depression and what I think about depression and what I think about mental illness more generally, before we get into the nitty-gritty of the talk, which is to understand how we might be able to use some of these techniques from different perspectives to understand depression and then later schizophrenia. So I always like to start talks, and certainly in mixed audiences, when I'm talking about depression, to understand the impact of depression. And I think it's really important for us to remain grounded here, because we're studying, in my group, what I think is an incredibly important problem. This is a really devastating condition, highly debilitating and highly costly to the individual and, of course, to society as well. So I'll put up some scary statistics, not all of which I hope you'll have heard before. And these are things that still shock me today. You probably, most of you know that it has this very high lifetime incidence. You might not know that it's life-threatening to the extent there are more deaths due to suicide and depression than are killed on our roads every year in the United Kingdom. Actually, about twice as many people. That's an astonishing statistic. Think about all of the money that's been put into road safety over the years, bringing down the number of deaths every year from somewhere around 8,000 in the 1970s to about 1,500 today. And the rates of death by suicide are largely unchanged during that period. This is a really serious public health problem. In the year 2000, so a long time ago now, the estimated cost of the UK economy was £9 billion a year. Of course, this is going to be much higher these days. That compares rather unfavourably to our current total science budget in the UK, which is £4.5 billion a year. So it's extremely costly from an economic perspective as well as a personal perspective. It has a massive effect on people's real-world function and the way they feel about their lives, much greater than other common medical disorders like angina, arthritis, diabetes, and anything else you might be able to name. And although we do have effective treatments, we have antidepressant medication, various different flavours, various different mechanisms of action. We have different psychological interventions, again, various different flavours, probably various different mechanisms of action. Most of those treatments are not effective in people who try them. So with an antidepressant drug, a very well-known study from about 10 years ago in America showed that only about 1/3 of people will get better the first time they try a course of antidepressant medication. Now, that's a shockingly low statistic. If that's what happens to you when you're going to be treated for other sorts of illness, you probably wouldn't be too happy about it. And even in the case of psychological intervention, probably only about 40 to 50% of people are going to get better the first time they try it. So although we can treat depression, we have a long way to go in terms of making life better for patients. And that's basically what the research in this area is all trying to do. And of course, I should pay tribute here to an amazing study that's going on at the moment, led by Andrew McIntosh in the audience, which is taking a very similar kind of approach to what we're interested in here in a very large sample as part of a birth cohort approach and integrating that with neuroscientific information. And I think these kinds of very large-scale studies, in addition to the kind of small-scale work that I'm going to talk about today, are going to be very important in the future in terms of informing the kinds of challenges that I've put up on this slide. So, what is depression? So I've put up a picture here of the famous DSM, the Diagnostic and Statistical Manual, which lays down the criteria for mental disorders. And depression is one of the major psychiatric diagnoses. It's not just feeling down. It has to have a everyday life impairment. You have to have a certain set of symptoms, 5 out of 9 of them, and I've listed them up here. At least one of them has to be low mood or anhedonia. And so the computationally minded amongst you will be starting to think now that there are a lot of different ways of being depressed. If you only need 5 out of 9, and some of these can go up and down, then you're starting to talk about numerous, in fact thousands of different combinations of symptoms. And that's actually really important to begin with, because a lot of this talk is going to be thinking about heterogeneity, individual differences. And the first individual differences that we could think about is actually individual differences in symptoms. So take 2 different patients. Patient A might have low mood, poor sleep, loss of appetite, feeling very guilty, unnecessarily guilty, feeling very anxious and agitated, and have suicidal thoughts. Very classic presentation for someone who suffers from depression. And then you might have patient B who suffers from anhedonia, which is a loss of interest or pleasure in previously rewarding activities, sleeping all the time, feeling very tired, psychomotor slowing, so moving much more slowly than normal, terrible concentration, another possibly classic presentation. But of course you'll notice that these 2 patients have not a single symptom in common, yet they can both be diagnosed under this same term of experiencing depression. And that tells you from the beginning that we're dealing with a very complicated problem here. If you can have 2 people whose symptoms are entirely different to each other, and they both get exactly the same diagnosis, we're probably dealing with something that's going to be very heterogeneous. There are probably going to be important differences between different individuals. And the issue that I'm going to raise here, and the issue which is what neuroscience in the area of mental health is really trying to grapple with at the moment, and over the last 5 years or so, this has really come to the fore, is that in mental illness, the diagnosis is the symptoms. So when we say something like, what causes depression, we're not asking that question in the same way as we ask a question like, what causes cancer, or what causes the flu. We are asking a question about symptoms, not about a biologically defined illness. And that's really important, because although we have this clinical heterogeneity, we almost certainly, which I've described here, we almost certainly have this mechanistic heterogeneity as well. And that mechanistic heterogeneity is one of the things that I'm really interested in, and we're going to talk a lot more about as we go through the talk. And so I wrote an article about this for The Psychologist, which is the professional magazine for clinical psychologists in the UK, a couple of years ago. And I called it, What Has Neuroscience Ever Done for Us? You probably can't see the title, it's a bit small in the bottom corner. And the answer that I came to in this article was that neuroscience has basically done nothing for the standard treatment of mental health problems. All of the brain imaging research, all the behavioral research that we're doing in human subjects, in actual depressed people, has had basically no impact on the standard treatment and management of people who suffer from depression. The only argument you could make would be in the area of drug development, basically. So all of this research that we're doing and trying very hard to find important insights into what's going on in the brain hasn't filtered through to the clinic. And I think one of the big reasons for that is because a lot of that research ends up looking very uncertain in terms of what we can end up concluding about what is going on. And part of the reason for that is probably because of this mechanistic heterogeneity. So what do I mean by mechanistic heterogeneity? Well, here's some mechanistic heterogeneity for you. Let's say you had 3 different patients, and they've got these various combinations of symptoms. Some of them got a sore throat, some of them have got runny nose, some of them have got headache, some of them are feeling very tired, some of them got a bad cough. Mechanistically, so clinically there's a certain amount of heterogeneity there, little differences between individuals. But mechanistically, there might be critical differences here. And if you don't pick up on those critical differences, then you're going to miss really important information in terms of the treatment. So I, for example, always tend to get sore throat and a runny nose if I pick up the common cold. But my wife will invariably suffer from a bad cough. Okay? That's exactly the same mechanism. We've got the same cold because one of us gave it to the other one. But one of us is expressing the symptoms in one way, and the other one is expressing the symptoms in another way. But we've both got the same fundamental mechanism which is driving that illness. And then there could be a third person who's suffering from a very similar kind of set of symptoms. I've put bad cough, sore throat, and headache up here, but I could have put a few more. But this is a streptococcal infection. This is a bacterium. So the treatments for these 2 individuals here are very different. 2 of them basically need to go to bed for a couple of days, drink hot fluids and largely rest, because it doesn't matter how many antibiotics we give them, it's not going to have any kind of impact because they're not suffering from any kind of biotic infection. They don't have a bacterium, they've got a virus, so the antibiotics aren't going to work. This is a big deal at the moment, and lots of stories in the press you'll see about people taking too many antibiotics leading to antibiotic resistance. So this is an important issue more generally in medicine. But this person, if they're really suffering from a streptococcal infection, that could be quite serious. If that progressed, then they could end up very seriously ill indeed. So they probably really do need an antibiotic. And if we don't know the underlying mechanism, in this case we don't know what the type of infection is, even though the symptoms look quite similar, we're going to find it very difficult to know what to treat, who to treat with what kind of intervention. In some cases, you just need to go to bed. In other cases, you need to take an antibiotic. This is mechanistic heterogeneity. Similar looking symptoms, but different things wrong, different types of pathology in different people. And that's what I think, and what a lot of people who do neuroscience research in this area is going on when we talk about a diagnosis like depression. It's very likely that we're talking about a kind of catch-all umbrella term which is masking, at the level of the brain, lots of different types of brain processes that are going wrong, often probably in subtle ways, that are resulting in the specific symptoms that an individual is suffering from. And that's part of what I think computational psychiatry is going to help us grapple with. So a different approach to mental illness, which started to be put forward in serious terms by people with lots of money, and a big funder in the United States especially, started to be put forward about 5 years ago by a guy called Tom Insel, who is the director of the National Institute of Mental Health, which is probably the world's largest funding agency in the area of mental illness. And he said exactly what I've been saying to you here. We have these catch-all umbrella terms which are based on the symptomatic definition, and if we just focus on those, if we continue to just focus on those and use these diagnostic criteria as we are at the moment, which only talk about symptoms, then it's going to be very, very difficult for us to make progress because we're going to be trying to treat people who have the same diagnosis, but they've probably got lots of different things going on mechanistically between different individuals. So this is the standard approach. We have our manual which lays down what the disorders are in terms of symptoms. We've got the list of symptoms. We check to see if the patient satisfies the symptoms, and then we decide on what treatment we're going to do. But it turns out that this is a very difficult decision to make. So if you had a choice to give a person a particular antidepressant or another one that's got a slightly different mechanism of action and targets another neurotransmitter system, just based on these symptoms, it would be very, very difficult to decide which drug to give to which person. Or maybe another question, should I give this person an antidepressant medication, or should I send them off for a course of psychotherapy? And you might think, well, psychotherapy's got to be a good idea, and that can't be too harmful. But actually, if someone isn't going to respond to psychotherapy, that's a lot of money for the NHS to invest in a person if that treatment is not going to be effective, because the clinical psychologist's time is going to cost a lot of money. And they're also going to have to turn up every week, and it's going to use up a lot of their time as well. And maybe they could have been just as well treated, or maybe even better treated, by an antidepressant drug. These are not decisions that we can make in a mechanistically informed manner in clinical practice today. This is an area where neuroscience has not had any impact. And that is what I argued in the article that I referred to earlier, which is that because we don't have the neuroscientific information, answering this question actually becomes extremely difficult. So the proposal on the table, and something, again, a lot of people, including several colleagues in this room are interested in, is trying to work out, well, what are the brain mechanisms, the candidate brain mechanisms that we think might be important in talking about these kinds of symptoms. And so I'm going to talk about different brain circuits today. I'm going to talk about different types of cognitive process as well. And I'm just taking the example of anhedonia, because this is the area where I've concentrated a lot of my research over the last 5 years. So the loss of interest or pleasure, even that symptomatic definition contains two different processes, right? There's interest and there's pleasure. There's being excited about something and there's actually enjoying something. They turn out to have completely different mechanisms at the level of the brain, completely different bits of neurochemistry involved in those. One of them is involved, has the dopamine system involved, and the other one has the opiate system involved. So even in that simple definition, we can already see kind of clinical heterogeneity which may map on to heterogeneity at the level of the brain. So we could be talking with anhedonia about your hedonic response, actually how much are you going to enjoy something, the expected value, how much you think you're going to enjoy something, the vigor or effort, how much work you're able to put into getting something, or value-based choice, your ability to weigh up different decisions. And we know that these are all controlled by a relatively circumscribed set of brain regions. And I've put up a couple of examples here, but these are not the only parts of the system. They involve things like the ventral striatum, which has been known for a very long time to interact with the dopamine system and probably produce these feelings of being excited or being prepared to put in effort or vigor in order to get something. And the orbitofrontal cortex, which is probably involved in encoding how much you think you're going to like something. And then another structure, which I'm going to talk about later, so I'll just highlight it here and then come back to it, which is called the Habenula. And this is probably very important in terms of, we think of anti-reward or punishment. So not liking something or thinking that something is going to be very aversive. And then as soon as you start thinking in this kind of way about mental illness, you start to realize that there are two things that could potentially happen in terms of what our diagnostic classification will end up looking like in the long term. So on the one hand, we might be splitters. That is, we might end up with subclasses, different individuals with basically the same kinds of symptoms or overlapping clusters of symptoms, but have very different pathophysiology going on at the level of the brain. That's similar to the kind of viral example, bacterial example that I gave before. But then there's also another intriguing and very important idea, which is that when we define these disorders, depression here, anxiety here, schizophrenia here, we haven't really carved nature into its natural forms. We have imposed, if you like, a categorical distinction on nature, but in reality, the brain circuits are not really falling along those kinds of lines. So it's very likely that these kinds of symptoms, which crop up in other types of disorders as well, particularly prominent in depression, are also going to be important in other disorders as well, and so are the same brain mechanisms. So if we take the example of schizophrenia, famous for things like hallucinations and delusions, but of course it has these pronounced negative symptoms. One of the negative symptoms of schizophrenia is anhedonia. Probably the same kinds of brain mechanisms are implicated in anhedonia and depression and anhedonia and schizophrenia. Certainly in Parkinson's disease, which is associated with a profound loss of the dopamine neurons in the brain, we see very, very high rates of depression, in particular with anhedonia. And it turns out that treating Parkinson's disease with dopamine medication, which controls the stiffness and the tremor, is also quite effective at treating the anhedonia, a line of research which hasn't really been pursued very much, probably in part because Parkinson's disease lives in the realm of neurologists and depression lives in the realm of psychiatrists. But the reality is that these are probably all brain disorders at the end of the day of varying different subtleties. Same in ADHD. ADHD medications also target the dopamine systems, things like boredom in ADHD. And then, of course, the opposite, possibly the reward system going out of control in mania, which is associated with a huge amount of goal-directed activity and risky decision-making, and in many ways the opposite of the symptoms that we see in depression. So we may well end up, at the end of this neuroscientific endeavour, thinking about, if not actually structuring clinical services, according to what the underlying pathology we think is going on. And here I've talked about how we might end up splitting disorders, but also how we might think about commonalities of disorder, commonalities of mechanisms across different syndromes. And the thing that's closest to this in the rest of medicine is the revolution that's been going on in cancer research over the last 20 years, whereas if you talk to a cancer biologist, they're not that interested anymore in whether you have a kidney cancer or a lung cancer or a mouth cancer. They care about the mechanism. They don't mind where the the cancer happens to be growing in your body, but if it is a p53 suppressor gene type cancer, and that can occur in the mouth and that can occur in the liver, you're probably going to end up needing the same kind of treatment. And that's how cancer biologists see the world of cancer nowadays. And of course, clinically, they're still managed according to the different specialties. But in terms of the way the science is thinking about it, in terms of the way that treatment development is going on, we're moving to the realm of thinking about mechanism. And I think that's what has to happen in the area of mental illness. And I think the computational approach could potentially help here. So I talked about this chap, Tom Insel, who about 5 years ago put forward this idea, the research domain criteria, which talks about linking across different levels of explanation, and also talked about this heterogeneity within disorders and possibly common links across disorders. And he put forward the idea that you have to be broad in your thinking about mental illness. You can't just focus at one level of explanation, which is something I completely agree with. We can't just think about the psychology. We have to also think about the neural circuits. We have to also think about the molecular and the genetic level. We have to think about the phenomenological level as well. So he proposed this kind of matrix, if you like, where you have a component process, normally couched in psychological terms, where you could map all the way from the genetic level all the way up to the phenomenology, or think about the ways of measuring this. And this is the famous research domain criteria, which much of American mental health research now has to fit into as a result of this political decision that they weren't going to fund research according to diagnostic criteria anymore. They're going to fund it according to this research domain criteria. And surely some people in the audience are going to think I'm making this up, but it's actually true. So if you go to the NIMH website and you look at the funding criteria, the $1 or $1.5 billion pounds of NIMH money that is devoted to mental illness in the US is now defined according to this kind of criteria, and not the symptomatic criteria that I talked about before. And I think this is a really important endeavour, but there are some things that are missing from here. And I would encourage you all just to very briefly think about what is missing from this kind of approach. And I'm going to come back to it right at the end and tell you what I think is missing and what I think computational psychiatry might add to it. Okay, so the answer will be revealed at the end. So that was the old NIMH director. He went off to work for Google, and then he went to work for another company, and now he works for a different company again. And he was replaced by this chap up here, Josh Gordon. And Josh Gordon also likes the RDoC. So this is politically very important because these people have enormous power. They can divert the funding. And this is going to set the agenda for what American mental health research is going to look like. And I used to give this talk and only quote Tom Insel, and now I get to quote Josh Gordon as well, because it turns out he likes this computational approach. So he wrote on a blog post, one of his very first blog posts when he came into this position, he wrote that the computational approaches will be useful in defining these domains, connecting them with the neurobiology and testing their clinical utility. And using computational techniques like clustering analyses or dimensional reduction techniques, we can examine the underlying structure of behavioral performance across different tasks. And this is quite important because what we talked about on the previous slide is basically what they call this top-down and expert-driven approach. But it may be that, just as we saw with symptoms, it may be that the experts in cognitive neuroscience don't really know how behaviors cluster with each other into natural biological forms. So his position here is that the computational approach is going to be really important. I'll give a couple of examples of that in a minute. Okay, so that's my kind of broad outlook on mental illness. And then I'm going to try and persuade you here that the computational approach can make an important contribution to this way of thinking about the huge, challenging questions that we have to deal with when we're studying mental illness. So put simply, computational psychiatry is the use of mathematical and computational techniques to address questions relating to mental illness. A very, very broad definition I've given you here, but I think that's fair because I think it should be broad. And you might be thinking to yourself, well, what types of questions is he talking about? And what sort of types of data? And is he talking about the genetic level or the psychological level or the neuroscientific level? What sort of level of explanation are we talking about here? And I would say all. So all questions and all types of data and all levels of explanation, because I think the computational approach has something to add in all of these. But today I'm going to talk broadly about cognitive processes and brain circuit processes, because those are the things, those are the areas in which this kind of computational approach has been brought to bear with the greatest amount of effort and I think the greatest amount of success in the last couple of years. But of course you could easily apply this kind of approach at the genetic and molecular level as well. And broadly speaking, there are two types of research in this area. One of them I call the data-driven approach, and the other one I'm going to call the theory-driven approach. And I'm going to talk about the data-driven approach first. And the data-driven approach is quite nice because it taps into what Josh Gordon was saying on those previous slides. And if anything is going to give us a kind of quick win, short-term positive impact on treatment or management of mental illness, then it's probably going to be the data-driven approach. But I think in the long term, the theory-driven approach is actually going to be more fruitful. So the data-driven approach basically involves classification. It involves the kinds of computer programs that all of the big IT companies in the world, and also your supermarkets and Amazon and Google, they're all trying to do. They're all trying to classify you, basically. They're trying to predict what your behavior is going to be in the future, and they're trying to subtype you. And that's what the data-driven approach is going to try to do. So it's often associated with this term big data, and typically it is agnostic to the theory or knowledge that we already have about mental illness from previous research. So that is, it just sees the data. It doesn't care where the data came from. It may have some labels to match the data up with, or it may not have some labels. It may just decide to do this in a sort of more bottom-up approach. And it produces classifications. It clusters people. And that could be really important for that thing that I talked about earlier, which is finding subtypes of illness. So that's the data-driven approach. Whereas the theory-driven approach uses existing knowledge, or in many cases existing hypotheses, to specify a theory mathematically in the form of what I'm going to call a generative model. That's an important term. And then test whether that model can explain the data that is thrown at it. And I will explain this more. It's going to seem quite opaque at the moment if you're not familiar with the general idea. I'll explain it more in a few slides' time. And I'm splitting them like this because, in principle, these are entirely compatible with each other. So from a mathematical perspective, actually, they would fit very well together. But that's only in theory. But in practice, people actually separate them. So the people who do the kind of big data, data-driven computational psychiatry approaches are not typically the same people who do the theory-driven computational psychiatry approaches. So for now, these are largely different literatures. But in the future, there's no reason at all that they couldn't be combined with each other. OK, so data-driven computational psychiatry. I'm going to give two examples. And one is very clinically oriented and very sort of easy to understand. And the other one is a bit more sophisticated and uses brain imaging data. And so broadly speaking, there are two ways that you can do these kinds of machine learning approaches. You can do what's called supervised learning, which is when you tell the computer what the labels are. So here's a good example, things like face recognition software. So a computer program that's been shown thousands, millions of faces in the past will learn to classify things that look like faces in the future. So here's an example of course, a very seasonal example, I now realize, of the classification system going wrong. And so that often uses technology like support vector machines, which are very effective at doing this. But there's lots of different approaches to do it, and all have their own acronyms. And then you can also do unsupervised learning. So that is, you show the machine, show the algorithm some data, and say, there may be hidden subtypes just sitting in here in a multi-dimensional space, which is too difficult for humans to wrap our heads around because it's hard to think in more than 3 dimensions. Just go and find the clusters in the data. So that's the unsupervised approach. So here you're telling the computer what the labels are, and here you're saying to the computer, I don't know what the labels are. Just go and find me the clusters, and I'll label them later. And so an example of this is famous in the machine learning world. This is Old Faithful, a geyser in an American national park, and it has 2 periods with which it erupts. One of them is a short period, and another is a long period. So if you're waiting for the geyser to come, you should know approximately you need to turn up this long, about 50 minutes after the last one, or this long, about 80 or 90 minutes after the last one. And this is a good example of when this unsupervised learning approach can work well, because the algorithm can easily find these 2 hidden populations in the data. OK, so this supervised learning approach has been applied in a recent paper in terms of predicting treatment response in depression. A really interesting question. And it used a convenient sample of data that were collected about 10 years ago, that same data set that I told you about before, where only about 1/3 of the people got better on their first antidepressant. So they had lots of information on these people, hundreds, or probably 150 variables across every single individual. They had symptoms, they had the demographic characteristics, so their age and their ethnicity and their social background, and lots and lots of data. And in this, they could just define people as being responders or non-responders to a very common antidepressant drug. This one is called citalopram. People use it over here all the time. But they could have done it, if this trial had been different and used a different drug, they would have done it using a different drug. There's nothing special about citalopram here. And then for those who are computationally oriented in the audience, they built a model, and then they did what's called cross-validation, which is to try predicting within the same sample whether their model is going to be successful. And then very importantly, they then did a bit of what's called external validation. So they take another data set very similar to this one, which the algorithm that they're developing has never seen before, and then see, can we get successful classification when we show the model some data that it's never seen before. Okay, and I'm not going to go into the technical details about exactly how this was done. If you're interested, then have a look at the paper last year in Lancet Psychiatry. And so the first thing they did is produce a list of the most informative features. So, here we are. They had 164 to start with, and they just reduced these down to 25 features that seemed to be important in a kind of initial first pass. Some of these are quite interesting. So one of them was the initial severity. You might think that is sort of obvious as a potential predictor of treatment response. If someone's quite severely ill to begin with, chances are they're not going to get better as quickly as someone who is less severely ill. But then another one was whether they're currently employed. That's the second most informative feature on the list of features. You wouldn't necessarily have thought that was quite interesting. And then a little bit further down, ethnicity, so whether they were black or African American, right? There are interesting features in the data here that wouldn't necessarily be obvious to you as a clinician unless you're really recording this stuff, very, very systematically, because these are rather subtle effects at an individual level. But they can add up and give us some predictive value altogether. And then they basically build this model. Here they're using this support vector machine learning approach. And they managed, in the training sample, so in this star D sample, they managed to predict with 65% accuracy whether a patient's going to get better from a citalopram treatment or not. And you might think that's not very good, and you would be right, because 65% is not really enough to inform clinical practice. But it's better than the clinicians predicted, because the clinicians could only get 49% accuracy, which is basically chance. So if you talk to a psychiatrist and you say, am I going to get better from citalopram, chances are they're going to have a very, very difficult time telling you. Whereas this quite simple approach to modeling, which just takes the, no mechanistic information in here at all. It's just taking the phenomenological data, so the symptoms people are actually experiencing, and a few demographic characteristics, actually you can get it 65% correct. And then to guard against this issue, which is called overfitting, which is that you get esoteric aspects of the data and just randomly contributing to classification accuracy, in this out-of-sample validation, which is another one called COMED using a drug called escitalopram, which is very similar to citalopram, they managed to achieve 60% correct. And this is really important because it shows that the finding holds up in a completely different context. But then very interestingly, in another arm of this COMED study, where they're using a drug which has quite a different mechanism of action, so venlafaxine plus mirtazapine, so not really focused on the serotonin system in the way that escitalopram and citalopram are, they couldn't use the algorithm to predict who was going to respond. So it shows a certain degree of mechanistic specificity as well. And I really like this study because I think it shows the potential of computational psychiatry. Because you don't just have to do computational psychiatry in complicated neuroimaging or genetic data. You can use this classification approach on any kind of data. And in this case, it seems to give quite a positive response. And I think Adam Checkrud, who ran this study, even developed an app where you can go in and type in all the information if you're someone who's experiencing depression, and then it'll tell you the probability that the model would assign that you're going to get better or not. There's a really interesting idea. Okay, so this is kind of the introductory approach to classification, and now I'm going to use a kind of more complicated one. But I hope everyone can already see the value in taking this kind of computational approach. So the second study I want to highlight here identified what they call biotypes of depression. And these biotypes of depression are basically signatures that you detect using an MRI scan, not using the anatomy of the brain, but instead the degree to which different parts of the brain tend to vary with each other in terms of their activation. So when we put someone in a brain scanner, we can measure the blood flow going to different parts of the brain. And in some parts of the brain, if they're active, then they'll tend to change the signal in the MRI scanner. So that's basically what you're measuring. And you can divide the brain into a couple of hundreds different regions and then look to see how those regions co-vary with each other, which is often interpreted in terms of how strongly connected they are with each other. And this is what you get. You get many, many different links between different regions, very different connection patterns. And this would just be an average across several individuals. And then each individual will have a slightly different signature if we were to plot it out like this. So that's the basic idea. So here, for example, you can see two regions which tend to co-vary very strongly with each other. Dorsolateral prefrontal cortex at the front of the brain and the posterior parietal cortex towards the back of the brain. So normally if one of these is active, the other one is going to be active, and if one of them is inactive, the other one is going to be inactive. So that's basically what you're plotting here for all possible combinations of the regions that they've used in this particular study. So far, so easy to understand, I hope. And then what they then do is what I call a partly unsupervised learning based on the patterns in this in these data in people who suffer from depression, and then try to do this clustering without telling the algorithm what the labels are. So previously we had the labels, and so we said to the computer, well, these are non-responders and these responders, and now please find out what the discriminating features are. And here we're just saying, we don't know what the labels are, please produce some clusters, and then we'll think of the labels later. And so that's what they did. So they initially identify a couple of, or several connectivity features associated with different types of symptoms using something called a canonical correlation analysis. And they've got several hundred patients here. You need lots of data to be able to do this well. And then they use two summary scores for clustering, which are based around the results of this particular analysis. And you can see the results here. So it may look like these are all falling into a cloud where everyone is from the same population, but in reality, these are separate clusters according to the algorithm. They've colored them in different colors, and then there are some gray ones in the middle who sort of lie on the borderlines. But what the algorithm is telling us is that these are really different populations. So this is the first thing they have to do. Now they've got these 4 biotypes, as they call them. And then they look in the brain and see how these biotypes differ from healthy volunteers. And they pick out these different connectivity patterns which seem to classify different types of patients. And this is really interesting because what they basically highlight is a set of connections that, using studies which have just averaged across all of these individuals, all of these subtypes, have often produced differences between patients and controls in these areas. But what this analysis is telling us is that when we look at studies like that, some people are contributing to a difference in one area of the brain, or one circuit of the brain, I should say, and other people are contributing to a circuit in another, a different circuit in the brain. So here we have the associations between the frontal cortex and the amygdala, which are very important in symptoms like fear and anxiety and worry. So you can see these picked out here. Whereas here we have the corticostriatal thalamic loop, which is probably very important in reward and reinforcement processing. And you can see that these only appear in this seems to be abnormal only in 2 of the subtypes of patients, and this one appears to be abnormal in another one, but also the same subtype of patient here. And they can use these patterns to understand what the different circuits are that may be contributing to symptoms in these individuals. And they do a variety of checks to make sure that these are reproducible and scan people on 2 different days and check they get the same kinds of results. And actually it looks like a very solid evidence base. So far this is not terribly clinically interesting because what have we got? Well, not an enormous amount. We've just got some clusters. But they then go on to show that which biotype you're assigned to then can predict your outcome from going through a type of treatment. In this case, they're using a type of non-invasive brain stimulation called TMS. And here the results are quite remarkable because if you're in the first biotype, so that's this one over here, it turns out that you've got a very high chance of responding to this TMS intervention, whereas if you're in the second biotype or the 4th one, you don't. And that's fascinating because the algorithm that produced that classification had never seen these data. It had never been told what these labels were in the first place. So we provided a mechanistic insight which has then independently managed to provide some interesting clinical information about the outcome from this clinical trial. And this was actually, it's in the same paper, replicated it in a second trial. And then the other thing that was interesting about this is it started to speak to this question of mechanisms across the definitional boundaries of the disorder. So it turned out that there were quite a lot of shared connectivity features with another disorder, generalized anxiety disorder, and none of these patients were clinically depressed. So if you had generalized anxiety disorder, you could also easily be categorized into either type 1 or type 4 according to these biotypes. If you try to do the same thing in schizophrenia, almost nobody gets classified into one of these 4 biotypes, suggesting that the connectivity pattern in schizophrenia is probably going to be something quite different again. So again, it's an interesting idea because it's shifting across these diagnostic boundaries and starting to tell us about the commonalities of mechanisms that might give rise to different symptoms, even in people who superficially look like, clinically, they present as quite different to each other. Okay, so that's the second example of the computational approach in the data-driven form. Okay, so now in the last part of the talk, I'm going to talk about the kind of research that I do, which is the theory-driven computational psychiatry, because we don't have access to these kinds of enormous data sets in my group so easily, but we can do these kind of studies on a relatively small scale. So what we do is use existing theory or knowledge to specify or test a mathematically precise hypothesis, and this is called the model specification. And typically we're doing this at the level of the behavior. So we're getting people to play a computer game, we're recording their responses, and then we're coming up with a way in which we think they have solved this computer game. Like, what are the kind of different processes that are important in playing this computer game? So this specification process comes first. We have to write down what the model is in a mathematical form. And then we have to estimate the model, and we do this by adjusting what are called parameters, which are constants in the model's equations, so that we can best fit the data that the actual individual has provided for us. Often we will do something called model comparison, where we build several competing models, and then we compare between them and try to find the one that's got the best explanatory power with the least amount of complexity, which is called parsimony normally in the field. And then we do model testing, a very important component, which is we check to see just how well the model recapitulates the pattern in the original data. And often that will lead us to build a new model because we'll find some kind of systematic error in the way that the model is producing the responses. Okay, so that's going to seem all rather abstract, so I like to give an example. So here is an example of a bit of modeling that was done 20 years ago, where it was identified that dopamine neurons in the brain corresponded to what are called reward prediction errors. And the model is very simple. The model is here, and it just says that what your response is, so the response that you get when you get something nice, is the difference between what you expected and what you actually got. So simple idea, that's the reward prediction error. Or to put it simply here, so delta, which is the prediction error, is equal to R, which is the reward you got, minus your expectation on the previous trial. And originally, people thought that dopamine just corresponded to getting something nice, so pleasurable event. And that's what happens here, where a monkey is given a nice reward, a squirt of juice in the mouth. So that seems to suggest, well, dopamine is doing something to do with positive outcomes. But if the monkey is expecting this, so if it's got a conditioned stimulus which is fully predicting the reward, then you don't see any kind of change in the dopamine neurons when you get the juice. And that's really important because it suggests that it's not just actually getting the juice itself. So this is equivalent to getting a nice surprise, like winning the lottery. So you're not expecting all that money, and then suddenly it comes in, and what a great result. And this is a bit like getting paid at the end of the month. You're expecting the salary to come in, and well, it's a little bit deflating. It's not that exciting when you actually get paid at the end of the month and you see the money in your bank balance. And this is like if human resources have messed up your contract and you're expecting to get paid at the end of the month, and then they don't give you the money, and that's obviously very disappointing. And then you actually get a dip in the firing of dopamine neurons. So this is the plus, and this is the equals sign, and this is the minus. And this is an important computational principle. But without this rule, without this mathematical statement for what prediction errors are, we wouldn't actually be able to identify what this was. So we needed this theory sitting behind it in order to be able to interpret this particular pattern of data. And 3 neuroscientists just earlier this year, 2 of whom my collaborators, Peter Dyan and Ray Dolan, and also Wolfram Schultz at the University of Cambridge, got the Brain Prize for this discovery, which is the biggest prize in neuroscience. So another example would be, let's say you're sitting in the restaurant and you have to decide, am I going to eat ice cream or fruit salad? You have to choose one of them. So if you always like ice cream, then you'll always like ice cream. That's fairly straightforward. So you could have one model that just, this person is always going to choose ice cream. That could be model 1. Or it could be that you always like ice cream, but you're a little bit noisy in your decisions. So you don't always make the decision according to what your internal preferences are. Sometimes you'll just randomly go for the fruit salad. So that implies a little bit of decision noise, and we can parameterize how noisy that decision-making process is with this with this parameter here, beta. Or we could say, well, what you're going to choose depends on what happened last time. So last time, if you had a really good experience with the ice cream, you will choose the ice cream again because it was delicious last time and it'll be delicious again. Whereas let's say you had the fruit salad, if it was pretty horrible last time in this restaurant, then probably you're going to avoid it next time. So that would imply a degree of learning over time and repeated experiences. So that could be model 3. And then we could have some kind of combination of these. This would be a learning rule together with a bit of noisy decision. So your learning, your choice depends on your experience, but you also have a certain amount of noise, or what sometimes is called exploration in this literature. Sometimes you just explore the other options. And then typically we would compare these models and find out which ones we fit best, and we can model hundreds of individuals and see how well we manage to predict their choices across many different samples of ice cream and fruit salad. And we can decide which of these models is best. And then importantly, we can estimate what these parameters are. So how noisy you are in your decisions. Are you always going to go for the ice cream if you really do like ice cream, or sometimes you're going to go for the fruit salad? Or let's say the ice cream was really good last time. Is that the only thing you're going to pay attention to? Or are you going to think about the ice cream 2 times ago and 3 times ago and 4 times ago? That's what this alpha parameter does here. It's the speed at which you learn. So this kind of alpha-beta learning model is very, very common in the literature. And so we use these kinds of approaches in order to interrogate the brains and the behavior of people suffering from depression. And as I mentioned before, we've got this symptom of anhedonia, which is important in loss of interest or pleasure. And this interest or activity cluster of symptoms seems to predict poor response to treatment, which is a really interesting and potentially clinically important finding. And we know what the brain systems are from many years of very careful animal work that guide this kind of processing. So things like reward learning, as I talked about before, or how much you actually enjoy something, or how much effort you put in. There is this clear system which even has a direction to the way the information is passed, which travels through different parts of the brain in the prefrontal cortex and in subcortical structures like the ventral striatum and the thalamus. And the information is traveling around in different circuits, and some of the information relates to this kind of very emotional experience, like actually enjoying the ice cream, and others relates more to the kind of cognitive experience and the actual motor responses that you're going to make. But the overarching pattern in the system is pretty similar. And then we know that this is innervated by dopamine, so that you can see that coming in one of the arrows here. And then it turns out that there is also this very important structure which hasn't appeared on this, so I'm going to put it in for you, which is we call the habenula. And the habenula is this kind of side structure that sits and turns out can control the activation of brain dopamine neurons. So I'm going to talk very briefly about this now. So here's the habenula in humans. You can see it's this very tiny structure buried deep within the middle of the brain. So what does the habenula do? Well, if the dopamine neurons do prediction error, the habenula neurons seem to do the opposite. So if you stimulate habenula neurons, it turns out you can turn off the dopamine neurons. And if you tell the monkey that something nice is about to happen, then the habenula neurons turn off. And if you tell the monkey something nasty is going to happen, in this case an air puff to the eye, then the habenula neurons turn on. So it seems to be doing the opposite of what these dopamine neurons are doing. And so this led to an important hypothesis in the field about 10 years ago, which is maybe the habenula is hyperactive in depression. Maybe it's constantly signaling that bad things are about to happen. And there was very little evidence on this. We and some other people had done some studies suggesting maybe there was this hyperactivity of the habenula in depression. And then in some animal models of depression, it had been suggested that maybe it was overactive as well. So we set out to test this hypothesis. And we used this very simple experiment, just like what you would do in an animal experiment. You show it some pictures, some stimuli, and then you give it an outcome later on. And here we were using electric shocks, and the subjects are lying in the scanner and they're looking at the screen. Or we might have been giving them money, so just saying you've won £1 on the screen. And we tested that the learning had happened as we expected. So I won't talk you through all of these, but these all indicate a successful degree of conditioning. And the thing that we're really interested in is the response to these negative stimuli here. So they predict when the person is going to get an electric shock. And we do this using a computational approach. So sometimes in this experiment we're giving people the outcomes they expect, and sometimes we're not. It's called a probabilistic task. And then we can look to see how the association of this abstract stimulus evolves over the course of the task. And again, this is part of a computational approach, again using this simple prediction error-driven learning rule which I explained in the last couple of slides. So sometimes the prediction is high and sometimes the prediction is low, and then we can see how that then corresponds to brain activation at the time of the cue. And this produced a very clear response in our first paper, just in healthy volunteers. And we needed to show this because no one had ever tried to do this before in the Habenula, showing that as the association with the electric shock got stronger and stronger and stronger, according to our computational model, the Habenula increased in its response. And we also found this was linked to the amount of inhibitory behavior that subjects showed, which I'm not going to go through now because I'm going to run out of time otherwise. But it was a very nice link back to the behavior. And then the experiment that we then did, which was in people who were depressed, came in with the hypothesis that we expect to see this hyperactivity of depression in the Habenula in depression. If the Habenula is just firing off all the time, maybe that gives an insight into why people have this very pessimistic attitude or constantly experiencing a kind of very negative emotional state. And the indices of conditioning from our behavior were very similar. We looked to see the anatomy of the Habenula, so its shape and its size, and we also looked at the baseline activity, if they're just lying in the scanner not doing anything, and we didn't find any pronounced differences between the groups. Though interestingly, we did find a negative correlation with anhedonia and the volume of the Habenula, but most interestingly, this is in both groups. So even in the healthy subjects, some of them suffer from anhedonia, and you can see it's a very similar kind of relationship in the two groups. The place where we found the most pronounced difference, which was in the activation, according to the association with the electric shock, was here, and it was in completely the opposite direction to what we had hypothesized. And one of my favorite results that I've ever got as a scientist, because it convincingly disproved our theory. Not only was it not hyperactive, so not only is it not different in this direction, going towards the top of the graph, it's actually significantly going in the opposite direction. So if anything, the Habenula is doing the precise opposite of everything that we had thought it was going to do in people suffering from depression. And of course, this is important because this is how science really works. Normally, we have an idea and we think we understand how the brain is working in depression, and then we suddenly realize that everything we thought was wrong. So now we get to conduct some interesting follow-up experiments and try and understand what on earth we think might be going on there, which, if there's time for questions afterwards, I'll be very happy to share with you further. I'm not going to expand here because I want to talk about one very final study using this computational approach, and then we'll be finished. So the last study that I want to talk to you about is one that focuses on a completely different area of schizophrenia and really understanding hallucinations in schizophrenia. And I thought maybe there would be some people interested in schizophrenia in the audience, so I thought I would include this because it's a really nice example of this theory-driven computational approach. And it was published just earlier this year by Phil Corlett's group at Yale. And again, it used this kind of conditioning approach, a very nice idea. So they just present these checkerboards here, and then every so often, different checkerboards are associated with a different probability of hearing a sound. And it's a kind of difficult sound to determine because they're hearing white noise all the time. And this is a difficult to discriminate stimulus. So sometimes it'll be really obvious and sometimes it won't be. It's like a kind of burst of white noise like you used to get on an analog tape, like a kind of noise. And they just have to say whether they detected it or not. And then at the beginning of the experiment, these are really strongly associated. So these checkerboards are really strongly associated with this white noise. And then gradually the association gets tailed off over the course of the experiment. So by the end of the experiment, they're hardly ever really hearing this. But nonetheless, people, after they've been through this procedure and they're lying in the scanner doing it, and it's difficult to do this discrimination, will see one of these checkerboards and they will report they actually heard something. So it's like you've conditioned a hallucination in someone. And it's apparently very effective, and you can do it in people who aren't prone to hallucinations at all. But if you do it in people who are prone to hallucinations, people who've got a diagnosis of schizophrenia, then you can induce this quite profoundly, and you can see this here. But very, very interestingly, you could also find people who hallucinate on a regular basis who don't have a diagnosis of schizophrenia because they still retain insight into their condition, but they hear the voices. It's just they don't have a diagnosis of schizophrenia, and they're not getting treated with medication or anything. And you can see them here. And this was one of the nice things about this study, is it used this design where you could cross two factors, whether someone had a diagnosis of schizophrenia with whether they heard voices or not, because there are also some patients with schizophrenia who do not hallucinate, and primarily their positive symptoms are in delusions. So they had a really nice study design. And you can see that the degree to which people would report that they heard these hallucinations was correlated with the degree to which they reported hearing hallucinations in everyday life. So there's a bit of validity, kind of ecological validity to the experiment. And then they fit this really neat computational model, which is called the hierarchical Gaussian filter, which has been used in quite a lot of different experiments in this area recently, which tries to determine a number of different levels of a kind of cognitive processing hierarchy, and then tries to determine on the basis of the responses people have given and how they evolve over the experiment, what must have been driving their inclination to say that they were really experiencing these perceptual stimuli when they weren't actually there inside the scanner. And I won't take you through the entire hierarchy, but it basically has this part at the top which says how quickly you think the environment might change. This is called volatility. Right down to the bottom, which is are you prepared to make a response to say something is there or not? And so it turns out that the very top part here is not associated with hallucination, so the volatility in the environment, how much things change in a kind of a moment-by-moment basis. This bottom part, how prepared you are to make a decision to say that something is there or not, were not associated with hallucinations at all. The bit that was associated with hallucinations is the bit in the middle here, which is the extent to which your previous expectation interacts with the actual sensory evidence that is coming in. So what you expected in comparison to what you actually got, which is quite similar to that idea of a prediction error that we talked about before. And this is where the hallucinators really differed from the non-hallucinators. So these are the two groups who hallucinate, and you can see that they have, in the model, a very high weighting of their expectation of what's going to happen, so their internal model of the world. So they're expecting to hear, because they've seen this fractal stimulus, the conditioned stimulus, a sound, and they use that in order to generate the percept much more strongly than the people who don't hear hallucinations. So one of these groups is actually patients with schizophrenia who don't hallucinate, and the other one is healthy people who don't hallucinate. And again, it's a really nice example of the computational psychiatry approach, because if they hadn't applied this kind of computational model, all they would be left with is this kind of pattern of responses, and they wouldn't be able to figure out, well, is this just due to the fact that people who hallucinate just more prepared to say yes all the time, or is it because they think the environment is changing all the time? But in fact, they were able to focus in and find a very specific area in the cognitive processing hierarchy which determines the relative weight of the actual evidence that's coming in, so what you actually heard versus your expectations. And that's really what seemed to discriminate the groups here. Okay, so I can see that I'm running out of time. I'm just going to come back to this RDoC picture that I talked about before and think about what computational psychiatry is missing. And I don't know what you've thought about it, but I'm going to talk about, or I'm going to just mention three things. The first is how we can actually move between these different levels of explanation. So this is really hard. So they set us this challenge, but actually moving from the physiological to the cognitive or the behavioral, that's conceptually very difficult. But in many ways, computational approaches give us the power to do that. Because something like a noise parameter, or something like the relative weighting of expectation versus actual evidence, or something like a learning rate, can live at multiple different levels in the hierarchy. It can certainly live in the kind of cognitive processing that we do, but it can live in the brain circuits as well, and it can even live at the synaptic level, the level at which the molecules are really interacting with the postsynaptic terminal. And so these kinds of parameters could potentially help us link between these different levels of explanation. The second thing it can do is actually bring in a role of the environment, because the computational psychiatry approach is all about what is actually happening to your brain, as well as the kind of simple biology of the brain, because our brains exist in the environment and they're constantly processing information from that environment. And if you look here, you will see the environment doesn't actually come in to the RDoC schematic at all. And I think that's a really important contribution that it can make. And the third thing it can do is that it can actually find categorical differences between individuals. So this RDoC approach is very much built along dimensions. It assumes that everyone just varies more or less, a little bit here, a little bit there. But it may well be that the brain really does exist in categorically different states, and that we do really have categories of pathology that drive different kinds of symptoms, and it's not just all dimensional. And the computation approach can also help us to pick apart those kinds of questions as well as giving us an indication of where things truly are dimensional. Okay, and just a few resources in this computational psychiatry area, which I don't have time to go through with you. So I'm going to stop there, and I'm going to thank all of the numerous collaborators and the people in my group who've, of course, done all the work, and my mentors and the funders for giving us the money to do some of these experiments that I've shown you. And thank you all very much for coming and for your kind attention. Thank you very much. Okay, and now I'm going to attempt to turn the lights back on. There we go. So I think we have the lecture theatre booked, right? So if people want to stay and ask questions, then I'm very happy to answer them. Or if people need to leave, then that's fine.
Yep. If you have to leave, we'll have a minute for people to slide in and out of the room. But plenty of time for questions. For those of you who don't have to rush off. And even though we're in a different building, we've got the same wine and cheese reception back at 7 George that we'll move to when questions are over. I'll even give you the mic. And then everybody can hear you. I got yelled at last time for not giving people the microphone. But it's too hard to pass around. But in this case, it's too easy to not. I don't usually have turnover. Okay, so while people are moving out, maybe we'll start the questions for people who are eager to ask and answer. I can pass the microphone here.
Hi. Yeah, just a quick question about the about causality, because I guess some of the things that you observe could equally be they could be mechanistically linked to the onset of depressive symptoms, or they could be the brain's response to depressive symptoms, I guess. How important do you think making that distinction is, and how do you go about sort of teasing apart whether something is cause or consequence when you're doing this kind of work?
So I can give a kind of philosophical answer and a practical answer. So the philosophical answer is that I think cause and consequence are very hard at the level of the brain. So even just thinking about this, whether the thoughts are a consequence of your brain or the brain is a consequence of your thoughts. So we think that we can think things deliberatively and then influence our brain activity, but we also think the brain activity causes those thoughts in the first place. I think there's a certain point at which we get into kind of philosophical gymnastics and it becomes very, very difficult to think about what the answer is. The more pragmatic answer is that in some cases we can see these kinds of changes in people who've recovered from depression and people who are at high risk of depression, and maybe in some cases we can find it in people who have actually developed depression and we've been lucky enough to be able to test them behaviourally or scan them at some earlier point in the context of an epidemiological study like the one that you run, of course. So I think the first thing that we always need to do is find out what the changes are, and they may be correlated with symptoms or they may not, but then to confirm that they're truly kind of part of the pathology, I think we need to look at people who aren't currently ill, but we assume their brain hasn't changed an enormous amount or isn't going to change an enormous amount. And that's limited to a certain extent because, of course, the brain is going to change during depression and then may result in vulnerabilities later on. But I think that's one way that we can do it. And a good example here is cognitive impairment in depression. So patients with depression score about half a standard deviation lower on any given neuropsychological test that you would care to throw at them, a bit like patients with schizophrenia, except it's not quite as severe. And if you look at people who've recovered from depression and they don't have any symptoms, they still score about half a standard deviation lower. And that makes me think that part of that cognitive impairment is an important part of the kind of mechanistic pathway to the symptoms, because it's still there even after people have got better.
Why on earth would habenula activity decrease in patients with depression?
So thanks very much for asking that question. I wish I had the answer. So I could go back to the slide. Maybe I'll just try and describe it. So I talked very briefly about one of the animal models that's used in depression and has been used a lot in antidepressant drug development, and it's called learned helplessness. So learned helplessness is if you're basically really horrible to an animal, so you put it in a chamber where the floor is electrified, and every so often you just turn on the floor and it gets a nasty electric shock and it has nowhere to go, right? So it cannot escape. And then you open an escape hatch in the side, and then you turn on the floor and it still doesn't escape. it sort of adopts this very passive approach, so the coping behavior as opposed to escape behavior. And so some animals with some animals will develop this kind of learned helplessness pattern, not all of them. But it turns out if you take animals who have developed learned helplessness, and if you interbreed animals who are very vulnerable to learned helplessness and end up with a strain that is very, very likely to show learned helplessness, even before you expose them to a stressful experience, you see this habenular activation. So there's something in the animal literature pointing us towards this idea about what's going on with learned helplessness. And so that's one of our clues, and I started thinking about our experiment afterwards. And basically what we do is we put the people inside the scanner, and we wire them up to an electric shock, and then every so often we give them the shock, and they're stuck inside the scanner, and they can't get out. And it made me start to think, well, maybe we're doing something quite similar to what's going on in the animal experiments, because they probably do feel quite, like they can't really get out. Of course, they could always press the alarm bell and come out, but in reality, no one really does that. So maybe we're putting them into a sort of learned helplessness scenario as well, and maybe that's quite different in the people who are suffering depression. Maybe they're more likely to do that. So a new idea that we're starting to test at the moment, we're just about to start an experiment, is the idea of this active avoidance. So maybe what the habenula is not just firing and telling you that something nasty has happened, but actually firing and also telling you to get out of there, to elicit an active avoidance response. And it may be that that is the thing that is not normal in depression, because that's what learned helplessness would look like if you didn't display this active avoidance tendency. So that's our kind of working model at the moment. But for all I know, it could be completely wrong. That's the best thing that we've been able to come up with so far. But thank you for asking the question. Sorry I don't have a good answer.
And if you put your hand up so I can see that you've got a question, I can stack you up in my mind.
Thank you. That pretty much lends into my question. What is the object of analysis for computational psychiatry? Because I think the story you told already indicates that it's very difficult to say there's something wrong in that one area.
Yeah.
Because you have to look at the context in which that area maybe does something very functional given the life circumstance of that animal. Is that part of the thinking of the field?
So absolutely. So you have to. So I talked about on one slide, what kinds of data and what kinds of levels of explanation and what kinds of hypotheses. And I do think that ultimately you have to try and incorporate them all. You have to, if you're going to have a computational explanation, you absolutely have to take into account the environment. The computational approach assumes that the brain is a data processing machine. It assumes that the information is coming in, the brain is constantly building models of what's going on, and then it's trying to produce appropriate behavioral outputs. That's a very kind of simplistic way of thinking about it. So you cannot ignore the environment. You cannot ignore the life experience of someone that someone has gone through to get to the point where they come to take part in your experiment. I'll give you an example of something we're doing at the moment. So we've got a fascinating study ongoing at the moment where we're trying to think about what computationally is the effect of having really horrible experiences when you're very, very young. So there are some children who grow up in very adverse life conditions. They have a very unstable home environment. They may be subject to abuse. And they are learning about the environment in a very different way to a child who's growing up in a stable household. And that is going to affect their estimation of what the environment is like. And we think one of the things it's going to do is change their estimate of how things are changing over time. Because if something's very volatile, then you might gradually learn over the course of the first 10 years of your life that in general things are very unstable. And if you come from a different household where things are very stable, you might learn generally things are stable. And then what happens when you go to school and then suddenly you have to move from this very unstable environment into a very stable environment? So you can think about a computational hypothesis that takes into account those kinds of experiences that kids have gone through. And I think actually that could be, those kinds of experiments are going to probably tell us some really interesting information. And they're obviously going to interact with many of the genetic liabilities that people have for depression as well. And it's hard to pick those apart sometimes. But I think it's a kind of it's kind of necessary that the environment is part of that computational explanation, because, and also at the neuroscientific level as well as at the psychological or phenomenological level. I think it has to be part of the explanation. And that's why I distinguished it from the RDoC in the slide towards the end.
Hi, John. You talked about anhedonia and schizophrenia in one of your slides, where one is within the realms of psychiatry and one in neuroscience.
Well, Parkinson's disease.
Right.
Parkinson's disease
Right.
is traditionally in neurology, and then schizophrenia or depression traditionally in psychiatry.
And then you ultimately said they could fundamentally both be issues of the brain, as almost suggesting them as a collective, right? My question is sort of where are these nebulous lines between the interdisciplinaries, and as we continue to develop more knowledge, in general, do you think those lines will fade into sort of one, like the brain as a subject, as opposed to the sort of does that make sense?
It does. So you're kind of leading me into a very provocative area.
Yes.
I'll have to give you a straight answer, because I think it's good to be honest. I'll just allude to my great colleague, Chris Frith, who people may have heard of, a great thinker in this area. And he says things are psychiatric disorders until we find an explanation for them. And then they cease to be psychiatric disorders. They get reclassified by medicine as something else. And I think that's a very provocative thing to say. He's trying to be deliberately provocative there. And he wrote that in a book review about the history of psychiatry. But to a certain extent, I think the basic point that he's getting at is that there are these arbitrary divisions according to the particular discipline of medicine you have to be in. And there are definitely cases on the border where it's very hard to know whether it makes sense for something to be in psychiatry or neurology. So why is it that schizophrenia, which most people think of as a kind of brain disorder, even though we don't really understand the pathology, is treated by psychiatrists, but something else like Tourette's syndrome, which has basically a behavioural component and largely behavioural diagnosis, is treated by neurologists? Why isn't that treated by psychiatrists? And then you start to think, well, maybe there are some kind of historical accidents that happened in the past. But I think that at the end of the day, these things that people experience, these symptoms, and whether you believe in disorders or not, we certainly believe in the symptoms, they all must come from the brain. I think the brain, so as a neuroscientist, I'm a materialist, so I believe that the subjective experience is caused by what's going on inside your brain. And as soon as you believe that, then neurology and psychiatry become this very blurred boundary, right? So depressions in Parkinson's disease is treated often by neuropsychiatrists who sit in neurological hospitals, and actually the overlaps are kind of there and apparent for everybody to see if you look hard enough. And hallucinations in Alzheimer's disease, and a certain amount of brain pathology in schizophrenia. At the end of the day, I do think that these are all brain disorders. It just happens that we can identify what the pathology is in many of the neurological disorders, not all of them. And we haven't got to that stage in psychiatry, probably in part because we are kind of using umbrella terms and putting a lot of things that are mechanistically separate together with each other. But I do think the point will come where we are able to identify, with as much certainty as a neurologist can about something like Alzheimer's disease, what the pathology is in this particular subgroup of patients. Because we used to have in neurology just a thing called dementia. And if you just thought about dementia, there'd be all these subcategories in there. And I think that's probably quite a lot what depression is going to look like as well. So yeah, I guess I'm a bit of a radical iconoclast in that sense. And I think that those boundaries are quite arbitrary.
Can you comment a bit about the Bayesian interpretation of those diseases? Because I think you commented the same. There is a model of schizophrenia which suggests that this is an over-reliance on priors, but I think there is an opposite hypothesis that says that schizophrenic people under-rely on priors because priors should, in a sense, give a reality check on their delusions. So can you comment on?
Well, yeah. So it's a very good question, and I'm going to give a bit of a cop-out answer because it's not my exact area of expertise, and this is a literature that is developing a lot. So there is certainly this idea that in terms of beliefs, patients with schizophrenia, they may under-rely on priors. On the other hand, you simultaneously seem to get this over-reliance on priors because delusions are by their nature persistent. So if something is very persistent, one assumes that there must be a strong prior, and it must be very, very precise. This is in the area of hallucination. So again, it's important to remember that the pathology of different symptoms, could potentially not overlap, though of course it could overlap as well. So all I can say is what the model showed in this case, right? So the authors of this study are very well aware of what the conflict is in the different hypotheses here. And what their model produces in these, not in schizophrenia per se, but in terms of hallucinations, this is really important because this group, the blue, do not have schizophrenia. but the hallucinations are associated with an over-reliance on the prior. So I think that's all that we can say from this. And I don't think it's a theory of schizophrenia. I think it's a theory of hallucinations, and there may be other theories of delusions. But there is definitely a conflict in the hypotheses in the literature, and I think it's something that, in time will probably be resolved, or maybe someone will come up with some grand overarching theory that explains how you can be simultaneously over-dependent on priors and the priors can be very weak all at the same time. But I haven't read anything yet that I find particularly convincing in that area. But it's a great question, and it's a kind of very active area of research at the moment.
I was wondering if we think about or talk about mechanistic modeling.
Yeah.
Do you think there could be highly nonlinear processes during brain function or during development that could limit our insights into the function?
So the simple answer is yes, right? So yes, the brain is very obviously highly nonlinear, and some of those high nonlinearities might look to us as though they are categorical differences. You could have a nonlinear process that just essentially appears to be different, a clustering difference. So I do think not everything is going to work along dimensions, and I do think there are things like critical periods during development, and that you may well end up with pathways that don't follow a linear approach. But there is also a limit to what data we can collect and what we can actually study realistically. So, we cannot realistically scan the brain of every person who is going to ultimately suffer from depression or schizophrenia right from the point where they're 2 or 3 years old, unfortunately, much as we would like to. So I think we have to make do with what we have and make certain assumptions. But I do think some of the things that are coming out of this literature, they do speak to nonlinearities in brain function and the ideas of clusters as opposed to, or categorical differences as opposed to dimensions. I think just because you go down the neuroscientific route doesn't mean that you have to throw away the categorical idea altogether. It doesn't all have to be, normally distributed at the end of the day. So I'm sorry it's not a terribly satisfactory answer to your question, but I agree it's very important. I just think it's very difficult for us to address in a satisfactory manner.
So I'm maybe overreading this, but it seems that there's a subtle difference between this last paper and its predecessors. And the predecessors that you spoke about were us imposing a model on the brain and trying to learn the parameters of those models, where this one looks as if it's kind of inverting that and saying the brain is looking at the world with a model.
Yeah, well, that's true, but that's what these other models are doing as well. So the other papers are imposing, if you like, this prediction error idea model, and then in many cases we can estimate the parameters. It's done in a slightly different format here, so the idea of the cognitive hierarchy, but you can apply exactly this kind of framework to simple reinforcement learning as well. It would work just as well.
Right, but having done that, then they suggest that the condition is related to overly strong priors. Did they hypothesize the symptoms of overly weak priors and whether that relates to a known condition?
So overly weak priors. So I guess if you had overly weak priors, you would just be updating all the time. If you started with overly weak priors, but you were able to make a prior, then you might be in a situation where you could be shifted a lot at the beginning, but then eventually you would settle or something. If you just had overly weak priors, full stop, then everything would be, you would just shift all the time, I suppose. I think that's what overly weak priors would look like. Your estimate of that component of the environment would just be moving about all the time. But I don't know what that would look like clinically.
Perhaps if you've got overly weak priors, you ask lots of questions.
Oh shit, sorry. So I had a question about, at the beginning of the talk you mentioned psychotherapy.
Yeah.
So I had a question around that. So just a very quick example, there's a guy at Berkeley who's interested in modularizing CBT, and so he's using ecological momentary assessment and then structural equation modeling to try and make CBT more personalized. And so in terms of the implications of the sort of computational approach, do you, I mean, and I don't know if this is controversial or not, but do you sort of see the future as being a phasing out of things like psychotherapy and a move more towards medication, or a bit of both, or what might the implications be?
No, absolutely not. I definitely don't think it's kind of phasing out of psychotherapy. It may well be that when we do things like, like non-informed classification, so the unsupervised learning that we talked about before, and we relate those kinds of clusters